Good morning. Today we're going to talk about augmenting data structures. And this is so normally, rather than designing data structures from scratch, you tend to take existing data structures and build your functionality into them. And that's a process we call data structure augmentation. And this also today marks sort of the start of the design phase of the class. We spent a lot of time doing analysis up to this point. And now we're still going to learn some new analytical techniques, but we're going to start turning our focus more to how is it that you design efficient data structures, efficient algorithms for various problems. And so this is a good example of the design phase. It's a really good idea at this point, if you have not done so, to review the textbook Appendix B. So you should take that as additional reading to make sure that you're familiar, because over the next few weeks we're going to hit almost every topic in Appendix B is going to be brought to bear on the subjects that we're talking about. And if you're going to go scramble to learn that while you're also trying to learn the material, it'll be more onerous than if you just simply review the material now. Okay, we're going to start by an illustration of the problem of dynamic order statistics. Okay, so we're familiar with finding things like the median or the kth order statistic or whatever. Now we want to do the same thing, but we want to do it with a dynamic set. Rather than being given all the data up front, we're going to have a set, and then at some point somebody is going to doing typically insert and delete, and at some point somebody's going to say, okay, select for me the ith largest guy out of the, or ith smallest guy. In the dynamic set. Or something like OS rank of X, okay, the rank of X in the sorted order of the set. Okay? So either I want to just say, for example, if I gave n over 2, if I had n elements in the set, and I said n over 2, I'm asking for the median. I could be asking for the min, could be asking for quartile. Here I take an element and say, okay, so where does that element fall among all of the other elements in the set? Okay? And in addition, these are dynamic sets, so I want to be able to do insert and delete. Okay? So I want to be able to add and remove elements. So the solution we're going to look at for this one, the basic idea is to keep the sizes of subtrees in the nodes of a red-black tree. So let me draw a picture as an example. Okay, so in this tree, okay, I didn't draw the nils for this. I'm going to keep two values. I'm going to keep the key, and so for the keys, what I'll do is just use letters of the alphabet. Okay, and this is a red-black tree, so just for practice, how can I label this tree so it's a red-black tree? So I haven't shown the nils. Remember, the nils are all black. So how can I label this? Red and black. Make sure it is a red-black tree. Not every tree can be labeled as a red-black tree, right? Okay, this is good practice because the sort of thing shows up on quizzes. Make F red. Good. And then everything else black. That's certainly a solution. Yep. Okay? Because then that basically brings the level of this guy up to here. Actually, I had a more complicated one because it seemed like more fun. Okay? So what I did was I made this guy black. Okay, and then these two guys red and black and red and black and red and black and black. Okay, but your solution is perfectly good as well. Okay, so we don't have any two reds in a row on any path, and all the black height from any particular point going down, we hit the same number of blacks, whichever way we go. Okay, so good. So the idea here now is that we're going to keep the subtree sizes. These are the keys that are stored in our dynamic set. We're going to keep the subtree sizes in the red-black tree. So that, for example, this guy has size 1. These guys have size 1 because they're leaves. And then we can just work up. Okay, so this has size 3. This guy has size 5. Okay, this guy has size 3. And this guy has 5 plus 3 plus 1 is 9. Okay, so in general we'll have size of x is equal to the size of left of x plus the size of the right child of x plus 1. Okay, that's how I compute it recursively. Okay, so very simple formula for what the size is. It turns out that for the code that we're going to want to write to implement these operations, we're going to, it's going to be convenient to be talking about the size of nil. So what's the size of nil? 0. Okay, size of nil, there's no elements there. However, if in most programming languages, if I take size of nil, what will happen? You get an error. Okay? That's kind of inconvenient. So what I have to do in my code is everywhere that size of nil, that I might want to take size of nil, I have to say, or take the size of anything, I have to say, well, if it's nil, then return 0, otherwise return the size field, etc. So there's an implementation trick that we're going to use to simplify that. It's called using a sentinel. Okay? A sentinel is nothing more than a dummy record. So instead of using a nil, we'll actually use a nil sentinel. So we'll use a dummy record for nil such that size of nil is equal to 0. So instead of any place I would have used nil in the tree, instead I'll have a special record that I'll call nil, but it'll be a whole record. And that way I can set its size field to be 0, and then I don't have to check that as a special case. And that's a very common type of programming trick to use, is to use sentinels to simplify code, so you don't have all these boundary cases or don't have to write an extra function to when all I want to do is just index the size of something. Okay, everybody with me on that? Okay, so let's write the code for OS select given this representation. And this is going to basically give us the ith smallest in the subtree rooted at x. Okay, so it's actually going to be a little bit more general. So if I want to implement the OS select I have up there, I basically give it the root and I. Okay? But we're going to build this recursively, so it's going to be helpful to have the node in which we're trying to find the subtree. So here's the code. Oops. Okay, so this is the code. And let's just see how it works, and then we'll argue why it works. Okay, so as an example, let's do OS select of the root and 5. Okay, so we want to find the fifth largest in the set. Okay, so we have OS select of the root and 5. Okay, so this is inconvenient. Okay, so we start out at the top. Well, let's just switch the boards. Here we go. Okay, so we start out the top, and I is the root. Okay, so excuse me, I is 5. Sorry. Okay, and the root. So I is 5. Okay, so we want to find the fifth largest. So we first compute this value k. Okay, so k is the size of left of x plus 1. What is that value? What is k anyway? What is it?
6.
Well, in this case, it's 6. Good. But what is the meaning of k? The order, the rank.
Yeah.
Good, good. The rank of the current node. Okay? So this is the rank of the current node. So k is always the size of the left subtree plus 1. That's just the rank of the current node. Okay? So we look here and we say, well, the rank is k. Now, if it's equal, then we found the element we want. Okay? But otherwise, if I is less, we know it's going to be in the left subtree. So all we're doing then is recursing into the left subtree. Okay, and here we'll recurse. We'll want the fifth largest one. And now, this time, k is going to be equal to what? 2. Okay? And now here we say, okay, this is bigger. So therefore, the element we want is going to be in the right subtree. But we don't want the ith largest guy in the right subtree. Okay? Because we already know there are going to be two guys over here. So we want the third largest guy in this subtree. Okay? So we have I equals 3 as we recurse into this subtree. Okay? And now we compute k for here. So this plus 1 is 2. Okay? And that says we recurse right here. And then we have I equals 1, k equals 1. And we return, in this code, a pointer to this node. Okay? So fairly okay, so this returns a pointer to the node containing h, whose key is h. Okay, and just to make a comment here, this we discovered k is equal to the rank of x. Okay, so any questions about what's going on in this code? Okay, so it's basically just finding its way down. Okay, the subtree sizes help it make the decision as to which way it should go to find which is the ith largest. So we do a quick analysis. Okay, so on a red-black tree, how long does OS select take to run? Yeah. Yeah, order log n if there are n elements in the tree. Okay, because it's red-black tree is a balanced tree, its height is order log n. In fact, this code will work on any tree that has order, log n in order the height of the tree. Okay, and so if you have a guaranteed height the way that that red-black trees do, you're in good shape. Okay, OS rank we won't do, but it's in the book. Also gets order log n. Okay, so here's a question I want to pose. Okay, why not just keep the ranks themselves? Yeah.
For algorithmic, is the argument x a key or the actual node itself?
It's the node itself. The node itself. Because otherwise you can't take left of it. Right? Yeah. I mean, if we were doing this in a decent language, strongly typed language, there'd be no confusion. But we're writing in this pseudocode that is good because it's compact, which lets you focus on the algorithm. But of course, it doesn't have a lot of the things you'd really want if you're programming things of scale, like type safety and so forth. Yeah?
Well, the reason we want to store it in the actual node is because it takes order by the time for insertion and deletion.
Yeah, that is, it's basically hard to maintain when you modify it. So, for example, if we actually kept the ranks in the nodes, certainly it'd be easy to find, the element of a given rank. But all I have to do is insert the smallest element, an element that's smaller than all the other elements, and what happens? All the ranks have to be changed. Order n changes have to be made if that's what I was maintaining. Okay? Whereas with subtree sizes, that's a lot easier. So this is because it's hard to maintain. When the red-black tree is modified. And that's the other sort of tricky thing when you're augmenting a data structure is you want to put in the things that your operations go fast, but you can't forget that there are already underlying operations on the data structure that have to be maintained in some way. Can we close this door, please? Thank you. Okay. So we have to look at what are the modifying operations and how do we maintain them. So the modifying operations for red-black trees are insert and delete. If I were augmenting a binary heap, what operations would I have to worry about? If I were augmenting a heap, what are the modifying operations? Binary min heap, for example. Classic priority queue. Who remembers heaps? What are the operations on a heap? Ooh, there's a good final question. Take-home exam, no, don't worry about it. Final, worry about it. What are the operations on a heap? That's right, just look it up on books times 24 or whatever it is, right? Answer man. What does answer man say?
Max or min, extract max.
Okay, and? So if it's a min heap, it's min, extract min, typical operations, and insert. Okay? And of those, which are modifying? Insert and extract min. Okay? So min is not. You don't have to worry about min, because all that is a query. So you want to distinguish operations on a dynamic data structure as those that modify and those that don't. Because the ones that don't modify the data structure, those are all perfectly fine as long as you haven't destroyed information. Okay, the queries, those are easy. But the operations that modify the data structure, those we're very concerned about, making sure we can maintain. Okay. So our strategy for dealing with insert and delete, in this case, is to update the subtree sizes when inserting or deleting. So for example, let's look at what happens when I insert k. Okay, element with key k. Okay, so I'm going to want to insert it in here, right? And so what's going to happen to this subtree size if I'm inserting k in here? Okay, this is going to increase to 10. Okay, and then I go left. This one's going to increase to 6. Okay, here it's going to increase to 4. Here, 2. And then I'll put my k down there. Okay, with a 1. Okay, so I just update it on the way down. Pretty easy. Okay, pretty easy. But, yeah. But now it's not a red-black tree anymore. Okay? So you have to rebalance. Okay? So you must also handle rebalancing, because remember, and this is something people tend to forget, so let me just, it's always, I think, helpful when I see patterns going on to tell everybody what the pattern is so that you can be sure of it in your own work, that you're not falling into that pattern. What people tend to forget when they're doing red-black trees is they tend to remember the tree insert part of it. But red-black insert, okay, that RB insert procedure actually has 2 parts to it. First you call tree insert, then you have to rebalance. Okay? And so you got to make sure you do the whole of the red-black insert, not just the tree insert part. So we just did the tree insert part. That was easy. Okay? But we also have to handle rebalancing. So there are two types of things we have to worry about. One is red-black color changes. Okay? Well, fortunately, those have no effect, right, on subtree sizes. If I change the colors of things, you know, no effect, no problem. Okay? But also, the interesting one is rotations. Okay? But rotations, it turns out, are fairly easy to fix up. Because when I do a rotation, I can update the nodes based on the children. I'll show you that. Basically, look at children. And fix up, in this case, in order 1 time per rotation. So, for example, imagine that I had a piece of my tree that looked like this. Okay. And let's say it was 7, 3, 4 are the subtree sizes. I'm not going to put the values in here. And I did a right rotation on that edge, okay, to put them the other way. Okay, and so these guys get hooked up this way. So always the 3 children stay as 3 children. We just swing this guy over to there and make this guy be the parent of the other one. Okay? And so now the point is that I can just simply update this guy to be, well, he's got 8, 3 plus 4 plus 1, using our formula for what the size is. Okay? And now for this one, it's going to be 8 plus 7 plus 1 is 16, or if I think about it, it's going to be whatever that was before. Okay? Because I haven't changed the subtree size with a rotation. Okay? Everything beneath this edge is still beneath this edge. Okay? And so I fixed it up in order 1 time. Now, there's certain other types of operations sometimes that occur where this isn't the value. You know, if I wasn't doing subtree sizes but was doing some other property of the subtree, it could be that this was no longer 16, in which case the effect might propagate up towards the root. There's a nice little lemma in the book that shows the conditions under which you can make sure that the rebalancing doesn't cost you too much. Okay? So that was pretty good. And so now insert and delete. That's all we have to do for rotations, are therefore still order log n time. Because a red-black tree only has to do order 1 rotations. Those normally take constant time. Well, they still take constant time. They just take a little bit bigger constant. Okay? And so now we've been able to build this great data structure that supports dynamic order statistic queries, okay, and it works in order log n time for insert, delete, and the various queries that you do. OS select. I can also just search for an element. So I've taken the basic data structure, I've added some new operations on it. Okay, any questions about what we did here? Okay, do people understand this reasonably well? Okay, so then let's generalize. Always a dangerous thing. Okay, so augmenting data structures. And so what I'd like to do is give you a little methodology for how you go about doing this safely. Okay, so you don't forget things. So the most common thing, by the way, people forget, I guarantee that on the, if there's an augmentation problem on the take-home, if there's one on the final, I guarantee that probably a quarter of the class will forget the rotations. Okay, if they augmented red-black tree, guaranteed. Okay, so anyway, so here's a little methodology to check yourself. So as I mentioned, the reason this is so important is because this is, in practice, the thing that you do most of the time. You don't just use a data structure as given. You take a data structure, you say, I have my own operations I want to layer onto this. So we're going to give a methodology, and what I'll do as we go along is we'll use the example of order statistics trees to illustrate the methodology. So it's 4 steps. Okay, the first is we choose an underlying data structure. Okay, which in the case of order statistics trees was what? Red-black tree. Okay. The second thing we do is we figure out what additional information we wish to maintain in that data structure. Which in this case is it's the subtree sizes. Subtree sizes is what we keep for this one. And, you know, when we do this, we could make mistakes, right? We could have said, oh, let's keep the rank. And we start playing with it, discover, well, we can do that, it just goes really slowly. So it takes some creativity to figure out what's the information that you're going to be able to keep. We're going to be able also to maintain the other properties that you want. Third step is verify that the information can be maintained for the modifying operations on the data structure. Okay, and so in this case, for red-black tree, for OS trees, the modifying operations were insert and delete, and of course we had to make sure we dealt with rotations carefully. And because rotations are part of that, we could break it down into the tree insert, the tree delete, and rotations. And once we'd done that, everything was fine. We didn't, for this particular problem, have to worry about color changes, but that's another thing that under some things, okay, you might have to worry about. Okay, for some reason, the color made a difference. Usually that doesn't make a difference. And then the fourth step is to develop new operations. Presumably that use the info that you've now stored. And this was OS select and OS rank, which we didn't give, but which is there, and which also it's a nice little puzzle to figure out yourself how you would build OS rank. Not a hard piece of code. Okay? So this methodology is not actually the way you do this. This is one of these things where, you know, so this is more like a checklist because, you know, you check, you see whether or not you've got some, you know, when you're actually doing this, maybe you develop the new operations first. You got to keep in mind the new operations while you're verifying that the information that you're storing can be here. Maybe you then go back and change this. And you sort of sort through it. This is more a checklist that when you're done, okay, this is how you write it up. Okay, this is how you say, this is how you document that what you've done is in fact a good thing. You have a checklist. You say, here's my underlying data structure. Here's the additional information I need. See, I can still support the modifying operations that the data structure used to have, and now here are my new operations, and see what those are. So it's really a checklist, not a prescription for the order in which you do things. You must do all these steps, not necessarily in this order. Okay, so this is a guide for your documentation. So when we ask for you to augment a data structure, generally we're asking you to tell us what the 4 steps are. It'll help you organize your things. It'll also help make sure you don't forget some step along the way. Okay, so I've seen people who added the information and determined the, developed new operations, kind of things, completely forgot to verify that the information could be maintained. Okay, so you want to make sure that you've done all those. So usually you have to play with interactions. Between steps. Okay, it's not just a do this, do this, do this. Okay, we're going to do now a more complicated data structure. It's not that much more complicated, but its correctness is actually kind of challenging. And it's actually a very practical and useful data structure. And I'm amazed at how many people aren't aware that there are data structures of this nature that are useful for them when I see people writing really slow code. Okay, and so the example we're going to do is interval trees. Okay, and the idea of this is that we want to maintain a set of intervals for example, time intervals. Okay, so I have a whole database of time intervals that I'm trying to maintain. So let's just do an example here. Let's see. Okay, so this is going from 7 to 10, from 5 to 11, from 4 to 8, from 15 to 18, 17 to 19, and 21 to 23. Okay, so this is a set of intervals. Okay, and if we have an interval I, let's say this is interval I, which is 7, 10, then we're going to call this endpoint, we're going to call the low endpoint of I, and this we're going to call the high endpoint of I. The reason I use low and high rather than left or right is because we're going to have a tree, and we're going to want the left subtree and the right subtree. So if I start saying left and right for intervals and left and right for trees, we're going to get really confused. This is also a tip, let me say, when you're coding, you really have to think hard sometimes about the words that you're using for things, especially things like left and right, because they get so overused throughout programming. So you know, it's a good idea to come up with a whole wealth of synonyms for different situations so that it's clear in any piece of code when you're talking, for example, about the intervals versus the trees, because we're going to have both going on here. Okay, and what we're going to do is we want to support insertion and deletion of intervals here, and we're going to have a query, which is going to be the new operation we're going to develop, which is going to be to find an interval, any interval, in the set that overlaps a given query interval. Okay, so I give you a query interval like, say, let's say, 6, 14, and you can return, this guy or this guy, this guy. Couldn't return any of these because these are all less than 14. So whatever, I can return any one of those. I only have to return one. Just have to find one guy that overlaps. Okay? So any question about what we're going to be setting up here? Okay. So our methodology is we're going to pick, first of all, step 1. Here's our methodology. Okay, so step 1 is we're going to choose an underlying data structure. So anybody have a suggestion as to what data structure we ought to use here to support interval trees? What data structure should we try to start with here to support interval trees? Interval trees. Anybody have any idea? A red-black tree, binary search tree. Yep, red-black tree. We're going to use a red-black tree. Oh, but I got to say what it's keyed on. So what's going to be the key for my red-black tree? So for each interval, what should I use as a key? Now there's a bunch of options here, right? So throw out some ideas. Always better to branch than it is to prune. You can always prune later, but if you don't branch, you never get the chance to prune. So generation of ideas. You'll need that when you're doing the design phase and doing the take-home exam. Yeah.
Left end of the interval.
Yeah, so we're calling that the low. The low endpoint. Okay. You can do low endpoint. What other ideas are there? High endpoint. Okay, now you can look at low endpoint, high endpoint.
Average.
Okay. Well, so between low and high, which is better? Yeah, that one's not going to matter, right? So doing high versus low, don't have to consider that. But there's another natural point to want to think about using, right? Like the median, the middle point. Okay, at least that's symmetric. Okay? So what do you think? Is that, what else might I use? The length? Yeah, the length. I think the length is not going to be, doesn't to me feel as productive. This is just purely a matter of intuition. Doesn't feel as productive because if I know the length, I don't know where it is. So how am I going to, that's going to be hard to maintain information about where it is. Where, for queries. So it turns out we're going to use the low left endpoint. But I think that it's, to me that was sort of a surprise that you want to use that and not the middle one. Because you're favoring one endpoint over the other. Turns out that's the right thing to do, surprisingly. Okay? There's another strategy, actually, there's another type of tree called a segment tree, where what you do is you store both the left and right endpoints separately in the tree, and then you maintain a data structure where the segments go up, where the line segments go up through the tree, one to the other. Okay, so there's lots of things you can do, but we're just going to keep it keyed on the low endpoint. That's why this is a more clever data structure in some ways. Okay. Okay, now this is harder. Okay, that's why this is a clever data structure. Okay. So what are we going to store in the So I think any of those ideas are good ideas to throw out and look at, and then you don't know which one is going to work until you play with it. So this one, though, is, I think, much harder to guess. You're going to store in a node the largest value, we'll call it M, in the subtree rooted at that node. Let's do it. Okay, so let me first, actually, so we'll draw it like this, a node like this. We'll put the interval here, and we'll put the M value here. So let's draw a picture. So once again, I'm not drawing the nils. So I hope that that is a search tree that's keyed on the low left endpoint, right? So 4, 5, 7, 15, 17, 21. Okay, so it's keyed on the low left endpoint. If this is a red-black tree, let's just do another practice. How can I color this so that it's a legal red-black tree? Not too relevant for what we're doing right now, but just I want to... Little drill doesn't hurt sometimes. Remember, the nils aren't there, and they're all black. And the root is black. I'll give that one to you.
The node at 511 should be red, and at 7.
Good. So this will work. Okay, so we go through a little puzzle. Logic puzzle. Okay, because this is really short, so it better not have any reds in it. So this has got to be black. And so now if I'm going to balance the height, I've got to have a layer of black here. It couldn't be that one. It's got to be these two. Okay? Good. Okay, so now let's compute the M value for each of these. So it's the largest value in the subtree rooted at that node. So what's the largest value in the subtree rooted at this node? 10. Okay, and in this one? 18. And in this one? 8. 18. Okay, that one's 23. That's 23. Okay, so in general, M is going to be the maximum of 3 possible values. Either the high point of the interval at x, or M of the left of x, or M of the right of x. Okay, does everybody see that? So it's going to be the M of x. For any node, I just have to look. What's the maximum here? What's the maximum here? And what's the high point of the interval? Whichever one of those is largest, that's the largest for that subtree. Okay, so the modifying operations. Okay, so let's first do insert. Okay, so how can I do insert? Okay, so there are two parts. First part is to do the tree insert. Okay, just a normal insert into a binary search tree. What do I do? I'm going to insert a new interval. Insert a new interval in here. How can I fix up the m's?
As you go down, you just check to see if the max of the interval you have is greater than the current maximum. You change it up.
That's right. You just go down the tree, and look at my current interval. And if it's got a bigger max, this is something that's going into that subtree. So if its high endpoint is bigger than the current max, update the current max. And just do that as I'm going through the insertion, wherever it happens to land up, in every subtree that it hits, every node that it hits on the way down. I just update it with the maximum wherever it happens to fall. Okay? Okay, good. So you just fix them on the way down. Okay? But we also have to do the other section. Okay? Also need to handle rotations. Okay? So let's just see how we might do rotations as an example. So let's say this is 11, 15, 30. Let's say I'm doing a right rotation. It's coming off from somewhere. Okay, where that's coming off from. So this is still going to be the child that has 30, the one that has 14, and the one that has 19. Okay? And so now we've rotated this way, so this is the 1115, and this is the 620. So for this one, I just use my formula here. Okay? I just look here and say, which is the biggest, 14, 15, or 19? 19. And I look here, which is the biggest, 30, 19, or 20? 30. Or once again, it turns out, not too hard to show, that it's always whatever was there, because we're talking about the biggest thing in the subtree, and the membership of the subtree hasn't changed when we do the rotation. Okay? So that just took me order one time to fix up. Okay. Okay, so fixing up, the m's during rotation takes one time. Okay? So the total insert time is order log n. Okay, so once I figured out that this is the right information, of course we don't know what we're using this information for yet, but once I know that that's the information, showing you that it works that insert and delete continue to work in order log n time is easy. Okay, now delete's actually a little bit trickier. So I'll just say it's similar. Okay? Because in delete, you go through and you find something. You have to go through the whole business of, swapping it with, if it's an internal node, you've got to swap it with its successor or predecessor. Okay? And so there's a bunch of other things that have to be dealt with, but it's all stuff where you can update the information using this thing, and it's all essentially local changes when you're updating that information. Okay? Because you can do it essentially only on a path up from the root, and most of the tree is never dealt with. Okay, so I'll leave that to you folks to work out. It's also in the book if you want to cheat. Okay, but it's good exercise. Okay, so any questions about the first three steps? Okay? Okay, fourth step is new operations. Okay, so let's see, I think we'll do that. Over here. Okay. So the interval search of I is going to find an interval that overlaps the interval I. Okay, so I here is an interval. Okay, got two coordinates. And this, rather than writing recursively, we're going to write it as it's sort of going to be recursive, but we're going to write it with a while loop. Okay, so it's equivalent. You could write it recursively. The other one that we wrote, we could have written as a while loop as well and not had the recursive call. So here we're going to basically just start x gets the root. Okay, and then while. We'll leave the comment for later. Okay. So that's the code. So let's just see how it works. Let's search for the interval. Let's search for the interval 14, 16. Oops. 14, 16 in this tree. Okay, so let's see. So it says x starts out at the root. Okay. And now while it's not nil, well, it's not nil because it's the root. And, well, what is this doing? Somebody tell me what that code does?
If the low of the interval is greater than the high, then you know it's completely to the left or can't be overlap.
Okay.
You're checking in either case to make sure that it still exists.
Yeah, well, so what is this doing? This is testing something between I and int of x. What is it? So int of x is the interval stored at x. Okay, what is this testing for? I hope I got it right. What's this testing for? Easy question, yeah.
Just if the interval you're looking at is below or above the interval in the root.
Above or below, so I need just simple words, simple words.
The test for overlaps.
Test for overlaps. In particular, it tests whether they do or don't. Do, don't, do. Test whether they, so if I get to this point, what do I know about I and int I, sorry, int of x, don't overlap. Okay? They don't overlap because the high of one is smaller than the low of the other. If the high of one is smaller than the low of the other, they don't overlap that way. Could they overlap the other way? No, because we're testing also whether the low of the one is bigger than the high of the other. So they're saying it's either like this or like this. Okay? Right? So this is testing not overlap. Okay. So that makes it simpler. So when I'm searching for 1416, I check here and I say, do they overlap? Okay, and the answer is, now we can understand it without having to go through all the arithmetic calculations. No, they don't overlap. Okay? If they did overlap, I found what I want. And what's going to happen? I'm going to drop out of the while loop and just return x. Because I'll return something that overlaps. That's my goal. So here it says, they don't overlap. Okay? So then I say, well, if left of x is not nil, okay, in other words, I've got a left child, okay, and low of I is less than or equal to m of left of x, then we go left. So what happens in this case if I'm searching for 1416? Is the low of I less than or equal to m of left of x? So low of I is 14. Okay? And I'm searching, and is it less than m of, is it less than 18? Yes. So therefore, what do? I go left. I make x point to this guy. Okay, now I check. Does it overlap? No. Okay, I take a look at the left guy. Is 8? I compare 8 with 14, right? And is it lower? No. So I go right. Okay? And now I discover that I have an overlap here, and it's overlaps. So it returns then the 1518 as an overlapping one. Okay, if I were searching for 1214, okay, if I'm searching for 1214, I go up to the top and I look. Does it 12, 14. Doesn't overlap here. I look at the 18, and it's greater, so I go left. Okay? I then look here. Does it overlap? No. So then what happens? I look at the left. It says I go right. I look here. Then I go and I look at the left. It says, nope, go right. I go here, which is nil. Okay? And now it's nil. I return nil. And does 12, 14 overlap anything in the set? No. So therefore, it always works. Okay? Okay. So we're going to do correctness in a minute. But let's just do our analysis first, so we don't have to do it, because the correctness is going to be a little bit tricky. Okay? So the time is order log n, because all I'm doing is going down the tree. So it takes time proportional to the height of the tree. Okay? So that's pretty easy. Okay. If I need to list all overlaps, suppose I want to list all the overlaps, how quickly can I do that? Can somebody suggest how I could use this as a subroutine to list all overlaps? Suppose I have k overlaps, k intervals that overlap my query interval, and I want to find every single one of them. How fast can I do that? How do I do it? How do I do it? After all, if I search a second time, I might get the same value. Well, how do I know it's... Yeah, there you go. Do what? Yeah, when you find it, delete it. Put it over on the side. Find the next one, delete it, till there are none left. And then if I don't want to have modified the data structure, insert them all back in. Okay, it costs me k log n if there are k overlaps. Okay, that's actually called an output-sensitive algorithm, because the running time of it depends upon how much it outputs. Okay, so this is output-sensitive. Okay, so you just completely... The best to date for this problem, by the way, of listing all is order k plus log n with a different data structure. Okay, and actually that was open for a while as an open problem. Okay. Correctness. Why does this algorithm always work correctly? So the key issue of the correctness is that I'm picking one way to go, left or right. And that's great as long as it's in that subtree. But how do I know that when I decide I'm going to go left, that it might not be in the right subtree and I went the wrong way? Okay? Or if I went right, that I accidentally left one out on the left side. We're always going just one direction. And that's sort of the cleverness of the code. The theorem is, let's let L be the set of intervals I prime in the left of a node X, and R be the set of I primes in the right of X. Okay? And now there are two parts I'm going to show. If the search goes right, then the set of I prime in L such that I prime overlaps I is the empty set. So that's the first thing I'm going to show. So if it goes right, then there's nothing in the left subtree that overlaps. So it's always, whenever the code goes right, no problem. Okay? Because there was nothing in the left subtree to be found. Does everybody understand that? Okay, what that says? I'm going to prove this, but I want to make sure people understand. Say, because the second one is going to be harder to understand. So make sure you understand this one first. Any questions about this? Okay. If the search goes left, then set of I prime in L such that I prime overlaps I empty set implies that I prime Okay. So what is this saying? If the search goes left, then if the left was empty, in other words, if you went left and you discovered that there was nothing in there to find, okay, no overlapping interval to find, then it's okay because it wouldn't have helped me to go right anyway, because there's nothing in the right to be found. So it's not guaranteeing that there's nothing to be found in the left, but if there happens to be nothing to found in the left, it's okay because there was nothing to be found in the right either. Okay, that's what the second one says. So in either case, you're okay to go the way that you're okay to go. Okay, so let's do this proof. So does everybody understand what the proof says? Because the understanding of the proof is tricky. It's logic. Logic is tricky. So suppose the search, we'll do the first one. Search goes right. Okay. So if left of x is nil, okay, then we're done. Since then we've proved what we want to prove. Okay, so if we go right, there's two possibilities when we go right is either we had left of x be nil or left of x is not nil. Okay, so if it's nil, we're okay because we said if it goes right, I want to prove this, that the things in the left subtree that overlap is empty. So if there's nothing there, there's clearly nothing there that overlaps. Otherwise, we have that the low of I is greater than m of the left of x. Okay? So if I look at x here, either x was nil in the while statement here. Either x is nil, or this is true. We just said it's not nil, so now let's take a look at, excuse me, I'm on the wrong line, here. So I'm in this loop, left of x was not nil, and the low of I was this, because I'm going, which way am I going here? I'm going right, so therefore this was not true. So either left of x was not nil, that was the first one, was nil, which was the first one, or low of I is greater than m of left of x. Okay, if I'm going right. Right? If I'm going right, one of those two had to be true. Okay, the first one was easy. Otherwise, we have this. Low of I is greater than m of left of x. Okay? Now, this has got to be that value, m of left of x, is the right endpoint, is the high endpoint of some interval, okay, in that subtree. So this is equal to the high of j for some j in L. So m of left of x must be equal to the high of some endpoint, because that's how we're picking the m's, for some j in the left subtree. And no other interval in L has a larger high endpoint than high of j. So if I draw a picture here, I have over here, I have I, and this is the low of I. And I have j, where we say its high endpoint is less than the low of I. So this is j, don't know how far over it goes. Okay? And this has high of j okay, which is the highest one in the left subtree. So there's nobody else who's got a higher right endpoint. So there's nobody else in this subtree, okay, who could possibly overlap I. Because all of them end somewhere before this point. This point is the highest one in a subtree. So therefore, I prime in L such that I prime overlaps I is the empty set. Okay? And now the hard case. Everybody stretch. Hard case. Okay, so does everybody follow this? So the point is that because this is the highest guy, everybody else has to be left, so if you didn't overlap the highest guy, you're not going to overlap anybody. Okay, suppose the search goes left. And that there's nothing to overlap in the left subtree. Now, as I went left here, but there's nothing, I'm not going to find anything. Now I want to prove that it wouldn't have helped me to go right. That's essentially what the theorem here says, that if I assume this, it wouldn't have helped to go right. I want to show that there's nothing in the right subtree, so going left was okay because I wasn't going to find anything anyway. So similarly, we go through a similar analysis. Low of I is less than or equal to m of the left of x, which once again is equal to the high of j for some j in L. Okay, so we're just saying if I went left here, if I go left, these things must be true. Okay, I went left. Okay, so since j is in L, it doesn't overlap I, because the set of things that overlap I in L is empty set. So since j doesn't overlap I, that implies that the high of I must be less than the low of J. Okay? So since J is in L and it doesn't overlap I, what's the possibilities? Okay? So we essentially have here, if I draw a picture, I have J and L, and I have I here. Okay? And the point is that it doesn't overlap it. Okay? So therefore, it must be to the left, because its low endpoint is less than left up. This low endpoint is less than this, but it doesn't overlap it. So therefore, its high endpoint must be left of the low of this one. Okay? Okay. But let me just take this one here. Now we'll use the binary search tree property. That implies that for all I prime in R, okay, everything in the right subtree, we have that low of J is less than or equal to low of I prime. So we're sorted on the low endpoints. Okay? So everything in the right subtree must have a low endpoint that starts to the right of the low endpoint of J, because J is in the left subtree. And everything in the whole tree is sorted by low endpoint. So anything in the right subtree is going to start over here. Okay, those are other things. These are I primes in R. Okay? We don't know how many there are, but they all start to the right of this point. So they can't overlap I either. Okay? So therefore, there's nothing. All the I primes in R that's also nobody. Okay, so just to go back again, so the basic idea is that since this guy doesn't overlap the guy who's in the left, and everybody in the right is going to be further to the right, okay, if I go left and don't find anything, that's okay, because I'm not going to find anything over here anyway. They're not going to overlap. Okay? So data structure augmentation, great stuff. Okay, give you a lot of rich data structures. Okay, built on, any ones hash tables, heaps, binary search trees, and so forth.